Okay, hey, so welcome back. This is our third lecture on our subatomic particles, or Unit 2. This is going to dive into some deep water. I'm just giving you a heads up. This stuff's going to take practice. This is going to be something that, let's just be honest, it can be very confusing. It's hard to visualize, it's hard to see. Because it's hard to visualize, that makes it a harder topic to understand. Nonetheless, we're going to attempt to work through this and try to figure these out. Today we're going to go over electron configuration. And our objective for today, or our goal for today, is to be able to identify and map electron positioning and spin within an atom. So we need to be able to determine not only where an electron is in an atom, but also whether or not it is spinning in a certain direction. So in saying all this, let's go dive into these deep waters and we'll see where we go. Okay, so what is electron configuration? Well, it's how electrons arrange themselves in each orbital. So how do they arrange themselves in each layer? How many electrons are present in each area? It allows us to know where valence electrons are and how they're spinning so we can predict how they're going to behave. It also allows us to determine the quantum number for a specific electron so we can pinpoint where we think an electron is going to be. So let's talk about trends. We've seen the periodic table before. We talked about oxidation numbers in our last lecture. Not only do we see the protons increase from left to right and from top to bottom, but we also see the electrons do that as well, because these electrons got to compensate for the protons to make them neutral. So, big thing from this periodic table. The farther right you go and the farther down you go, the more electrons you are going to deal with. So what are orbitals? We talked a little bit about the different layers that electrons can have, and we talked about the valence orbital, the valence shell. Well, let's dive into this. Let's get this a little bit more. We can think of orbitals as subsections of layers of the electron cloud. So we have all these different levels of the electron cloud. An orbital is just basically a subsection of that level. Each orbital can carry a specific number of electrons. So think about this. Okay, this might be just stretching out there and trying something, but you have a car. Okay, that car can carry 4 people on it or 5 people in it. Okay, each person in that car can carry X amount of items, whether that's phones or wallet, whatever it is. Each person can carry a certain amount of that. Think of this the same way. Our layers have subsections called orbitals. These orbitals, each of the orbitals can carry a certain amount of electrons. Okay? We identify these orbitals with lowercase letters, such as S, P, D, and F. Okay? So we have these certain orbitals, these subsections, that can carry only a certain amount of electrons in each subsection. And they're labeled S, P, D, and F. Each orbital has a specific number of electrons that they can store. So our S orbital, okay, it has one suborbital or one level underneath it. In that level, it can carry 2 electrons. So S orbital, first one you'll see, 1 suborbital, 2 electrons. Our P orbital, you get 3 suborbitals with your P orbital. Okay, those 3 suborbitals can each hold 2 electrons, giving us a total of 6 electrons. Okay, so p orbital, 3 suborbitals and 6 total electrons. Then we got our d orbital. That has 5 suborbitals, or 5 places it can store electrons. Okay, since each place can hold 2 electrons, that's going to be 10 total electrons. So that's S, P, D. Now we're at F. Your F orbital is your largest orbital. It has 7 subsections or suborbitals. Each of those subsections can hold 2 electrons. So we have 7 subsections, 2 in each of them. That can be a total of 14 electrons. Between all those orbitals, we can account for every element on the periodic table. So now that I've talked about one of the specific types of orbitals, let's just look back at our periodic table and let's see just where these orbitals are and see the trend that goes with them. So our first 2 columns, starting with hydrogen and beryllium, okay? those first two columns are going to be our s orbitals. Okay, so those are going to have s orbitals as your outermost layer, or your valence layer. So the ones to the right of the periodic table, that right side, that right section, that's going to be your p orbitals. Remember, p orbitals can have 3 subsections for a total of 6 valence electrons. Okay, our transition metals, or our middle group, they're always going to have a d orbital as their outermost layer, or their valence layer. And then finally, your lanthanides and actinides. I know we haven't talked much about those. Those are basically the section at the bottom of your periodic table. It's like they took a chunk out of the periodic table and put it on its own island. They are all going to include what we call an f orbital. Okay, that's where your 7 subsections, 14 total electrons can happen. So if we just look at the periodic table and we get an element within these sections, we can be like, okay, we know what the outermost orbital is already going to be. So now that we know where the electron orbitals are, how many electrons are in each orbital, or how many each orbital can theoretically hold, okay, and we know that the valence shells are located, where the valence shells are located, we can talk about how to identify specific electrons in atoms. Okay, let's talk about the element aluminum. Aluminum's atomic number is 13. So if it's neutral, that means it has 13 protons, but also 13 electrons. We're going to be mapping the electrons here. So now we need to come up with a map to locate all these electrons, or to account for all of them. The easiest way to do this map is to draw out this diagram, and I don't even know, a triangle, whatever you want to call it, but just follow with me here. I'll be showing you on the screen. This is probably, bar none, the best way to do this. Okay, so we start out with this diagram at the very top with 1s. Then we go straight underneath it and go 2s and 2p. Then the next row down we do 3s, 3p, 3d. And the following row underneath it, 4s, 4p, 4d, and now 4f. Following row underneath that, 5s, 5p, 5d, 5f. And then the sixth one underneath it just goes 6s and 6p, and 7 goes 7s and 7p. Okay, so now that we have those written out, okay, we have this really weird diagram written out. Now we can go through and assign our valence electrons. We are going to do this by following the arrows that are going to be drawn on now. Okay, so we start up at our top, at our s orbital. Our s orbital, 1s, can hold 2 electrons. So s holds 2. So we've got rid of 2. Now that gives us 11 electrons to deal with. Okay, so we're at 13. We minus 2 from your one that went into the s orbital. So we've got 1s, we got rid of 2. Now we're going to go down to 2s. Okay, 2s has 2 more. So now we've gotten rid of 2 more. So we had 13, we subtracted 2, then we subtracted 2 more. Now we're at 9 valence electrons. So right now our map says 1s, 2s. Now we can move on to our p orbital. So this will be 2p. Remember, we can have up to 6 electrons in the p orbital. So there we go, is we minus our 6 electrons from there. And now we went from 9 down to 3 electrons. So now we have 1s, 2s, 2p. Our next thing, if we follow the arrow down, we're going to have 3s. Okay, s can have 2. So we do that. Now we have a total of 1 electron left because we had 13 and we minus 2 from the first s. We minus 2 from the second s. Then we minus 3 from our row 2p. And then now we minus 2 from our row 3s, giving us a total of 1 electron left. That means we need to at least go into the 3p form, or 3p orbital. So that gives us our electron configuration of 1s, 2s, 2p, 3s, 3p. I know that sounds just kind of just like, what the crud, what just happened? But just follow with me here. The whole reason we do this is so we can map our quantum number. Okay, Our quantum number is basically our point in which we say, hey, your electron is at this point. Okay? So that's where our 1s and all that's about to play in. So, in our quantum number, okay, we must include our orbital, our subsection, and the number of electrons present in that subsection. Okay, so this is where our counting came in handy from earlier. So I know we said 1s, 2s, 2p, 3s, 3p, but now we got to add a exponent to it. The exponent is going to be how many electrons are in each orbital. Well, we're going to start from our innermost orbital, or one orbital, and those are going to be fully filled until we get to not having any more left. So we start out 1s, it can hold 2, or that would be 1s2. We also fully filled our second s, so that'd be 2s2. We again fully filled 2p, so that'd be 2p, and because it can hold 6 electrons, it'd be 2p6. Then we go back down to 3s. It can hold 2 electrons in its suborbital, so we have 2. So at this point, we've accounted for 12 electrons. Remember, aluminum has 13. So we have one more electron to deal with, and this is where our 3p came in, and we have 3p, and we only have 1 electron in this shell, so it would be 3p1. That would give us our total quantum number as 1s2, 2s2, 2p6, 3s2, 3p1. Notice, here's a key hint. All of the numbers in the exponent equal the number of electrons in that element. So, if you add up all those numbers and it's not the number of electrons in that element, you've misdone something. You've either added too many electrons, or you've taken too many away, or you just need to keep going with it. Okay? So that's the quantum number. Told you, we're diving into some deep water. Now, we're going to go this a step farther. If you weren't confused already, we're going to throw spin into it. If you didn't know, electrons can spin. They can spin either in the positive direction or the negative direction. We quantify that numerically with a positive 1/2 or a negative 1/2. We also show this visually by having an up arrow for the positive direction and a down arrow for the negative directions. Okay, when mapping electrons, it is not only important that we know where the electron is located, in other words, what orbital it is in, but if we want to be specific with this, we need to know how much spin or what kind of spin each electron is going to have. So, let's talk about orbital spin. Typically, each subsection of an orbital is going to have half their total number of electrons as positive or upspin electrons, and half of them as downspin or negatively spinning electrons. Each positively spinning electron can only be paired with a negatively spinning electron. So we can't have 2 up arrows right next to each other. This will, again, be evident in a second. Okay? Each subsection must fill their positively spinning arrows first. So you must first be able to fill all the upspinning arrows. Okay, or upspinning electrons. Okay, so back up. What is this? So we've mapped out all of our electrons in an atom. Now we're trying to identify a specific electron with its spin in an atom. We know that upspin is positive, downspin is negative. Okay, we know that each orbital can carry half its positive electron or positively spinning electrons and half negatively spinning electrons, and that positively spinning and negatively spinning electrons pair together. Okay, in each spot. Think about it again, back to our car. Okay, each person can carry maybe a phone and a wallet. Okay, they have a phone, a positively spinning electron, and a wallet, a negatively spinning electron, and they can only take up a certain spot in the car. So as we stated, each subsection must first have their positively spinning electrons filled before they can fill their negatively spinning electrons. So let's look at a p suborbital with 4 electrons in it. Remember, we can have a total of 6 electrons. So that means it has 3 subsections in it. Okay? If we fill up our positive or upspin electrons first, 1 in each section because it can't be paired with itself, then we have 3 positively spinning electrons, 1 in each section. Well, we have 4 total electrons, so we need at least 1 negatively spinning electron or downwardly spinning electron. We're going to pair that with 1 of the positive spinning electrons and put it in one of those spots. This lone electron will go to the first available negative spot in the orbital, giving us a complete map of the electron with its spin. So basically, what have we done here? What has this whole big, complicated ordeal taught us? Well, first, mapping electrons is hard. But we are now able to take a specific element and map every electron on it. And then if we want to say this specific electron number, whatever, on whatever orbital, we can say if it's going to have a positive or negative spin, or in other words, it's going to be spinning upwards or downwards. So basically, this took a really broad thing of having an element, and we broke it down to subatomic particles and was able to identify specifics about those particles. I hope this helped you out and gave you a better understanding of electron configuration. I understand if you are confused at this point. It's not an easy topic, okay? Especially for high schoolers, it's not an easy topic. So if you need to review the practice problems I'll have on, please do. That's going to help you. Repetition's just going to make it easier. In saying all that, keep up the good work in your classroom, and I'll see you later.